So there's three ways we classify stars: size, temperature, color, brightness. I guess mass could be included in size, not just volume, but how much stuff is inside a star. Now, not all stars are the same brightness, and for good comparison, just look out into the night sky, and you can see maybe a few hundred stars, and if you go somewhere dark, maybe a few thousand stars. But here's the thing: most stars you can see with your eyes are actually really close to us in our galactic neighborhood. And even the stars you can see, they're only like the brightest stars out there. Even our closest star, Proxima Centauri, you can't actually see with your eyes, even though it's the closest. So brightness is one of the huge variations we can see in the night sky. There's brighter stars, there's dimmer stars, there's some stars we can't even see even though they're close to us. And there's some stars that are really bright, but they're really, really far away. Now, let's go into like life cycle. What's the very beginnings of a star? So all stars that are being made now in our Milky Way galaxy come from nebulas. Now, you might be seeing them called planetary nebulas. You might see them called solar nebulas. Just know they're basically the same thing. As long as you see nebula, you know it's a cloud of gas and dust. And that's where the gas for new stars comes from. Now, nebulas tend to be really, really cold. They're some of the coldest objects out in the galaxy. And negative 250 Celsius is almost absolute zero, a couple of degrees away from it, 23 degrees to be more specific. And they can even be colder than that. That's really, really, really cold. Now, a brown dwarf, yes, it could be the start of a new star, but a brown dwarf can also just be a failed star. So what I mean by that is a brown dwarf, think of it like a bunch of Jupiters crammed together in one area. And if that brown dwarf doesn't get more mass, then it will just kind of just sit there and cool down for the rest of time. Now, brown dwarfs are weird in that they're very dense objects. So let me show you what I mean by that. So here's Jupiter for comparison, and here's one of the smallest stars that are possible, a red dwarf. In the middle, we have a brown dwarf. Now, imagine one Jupiter weighs one Jupiter, right? But this thing can have up to 79 Jupiters inside of it and still be about the same size. So what's going on here? Why isn't it way bigger than one Jupiter? Shouldn't it be like 70 times? Shouldn't it take up the whole screen, being 79 times more massive than Jupiter? Well, here's the thing. Because it's got no fusion to push out, all it does is as you add more mass, gravity just pulls it in and pulls it in and pulls it in and pulls it in more. So even if you were to throw more Jupiters into this thing, gravity would just crunch them closer together. It would compact it. And what that does is actually heat up the brown dwarf more and more. So as you add more mass and more Jupiters and more mass and more mass, it'll actually get hotter and hotter inside the brown dwarf. And if it gets hot enough and has enough mass, you can actually turn that brown dwarf into a small star. Now, the only reason the small star is bigger than the brown dwarf, because more gravity should pull it closer together, is actually fusion pressure. The heat of fusion pushes it out. So it pushes a small star out and makes it bigger than the brown dwarf. And you'll see that as you learn more in these notes, that fusion can actually make a star really, really, really big. But anyway, so that's brown dwarfs right there. Let's talk about stars. So those two things we just talked about, those were stellar objects. Now we're talking about actual stars. So a star can be considered on its main sequence if it is fusing hydrogen. So we call the main sequence basically the lifetime of a star, like its life. If it's not on the main sequence, it's almost pretty much dying. I'll put that in this perspective for a little bit. So main sequence stars, what happens is they generally remain around the same size for their entire life. Fusion pressure, the heat of the star pushes it outwards. Gravity wants to collapse it inwards. And they remain about the same. And that's good because if our sun was getting too terribly much bigger, it would kind of heat up the earth and, boil away our oceans and kill all life on earth. So that's not a good thing, right? It's good that stars remain in equilibrium. Now, main sequence stars have a huge size range. Stars on the main sequence fuse hydrogen, except the very, very biggest stars, that's pretty much 99.99% of all stars, is they're on the main sequence and they're fusing hydrogen. Once they run out of hydrogen and they start fusing helium or die, they're not on the main sequence anymore. Okay, so that's for everyone else who didn't answer that. All right, so lifetimes of stars. Let's talk about that for a minute. So a star's life is based on how much stuff it has. Now, it's not like most things in life where you think, okay, if I've got a full fuel tank in a car or something like that, I can go farther. Well, with stars, it's kind of the opposite. The more fuel they have in the tank, the shorter they live. It's more like a bonfire. If anyone's ever been to a bonfire, if you have a little small fire it burns slowly. You can use your fuel very, very slowly. If you got a giant pile of wood and you light that thing on fire, it's out within like 30 minutes. And stars are a lot like that. The more stuff a star has, instead of using that fuel over a longer period of time, it just burns it more quickly. And you can see that in this chart down here. A star with 60 solar masses will use through all of its fuel in 3 million years, whereas a star with 6 times less mass will last 10 times longer. And a star with 10 times less mass than that will last 30 times longer. And a star that's only zero 0.1 solar masses will last a trillion years or even longer than that. So the less hydrogen a star has, the longer its life. And that's because the smaller stars just burn fuel very, very, very slowly. There's also other factors like mixing of the core, but I'm not going to go into those. Just remember, more mass, shorter lifespan, less mass, longer lifespan. Now let's talk about the smallest stars out there, the red dwarfs. And actually our nearest star to us is a red dwarf. Now they range in size from about 7% sun's mass to about half of the mass of the sun. So our sun compared to a red dwarf is pretty big, actually. And these stars are actually really dim. So even though they're about 7% to 50% our sun's mass, as far as brightness goes, they're like less than a 0.1% all the way up to 7% as bright as the sun. So really, really not bright at all. In fact, if you were to take this smallest red dwarf, the 0.015% as bright as our sun, and put it where the moon was, like let's assume the outer edge was where the moon was, it would only be about 30 times brighter than the full moon. It would actually be really, really dark at daytime, whatever daytime was when the moon was nearby us. So yeah, these things aren't that bright at all. And I mentioned that you can't even see our closest stellar neighbor, Proxima Centauri. You really can't. It's really, really dim. With binoculars or a telescope, you could, but not with your naked eye. So here's what a red dwarf looks like with an actual telescope image. This is Gillespie 623b. It's not the closest one, but it's not too terribly far anyway. And you can see it is red in color, and there is some stuff coming off it that would probably be considered the star's corona. It does have all the layers, just like our sun does. But with red dwarfs, they last longer, and they also have a different ending than our sun does. I'll go in more on that later. Now, let's talk about the biggest stars. So we go from the smallest to the biggest. We have giants. So giant stars, they're the stars that, what happens when the star runs out of hydrogen? When it exits the main sequence, it can become a giant. Now, our sun will eventually become a giant, and you can see down here, it will swell to about 100 times its size once it's a red giant. So they get really, really big at the end of a star's life. Now, there's regular giants and then there's super giants. So let me talk about that for a second. So regular giants, you have a medium-sized star. At its end of its life, it starts fusing helium, which makes it hotter. And so that extra heat expands the stars out. Great. But really, really big giants, super giants, well, here's a couple right here on this image right here. Not only do they, when they reach the end of their life, do they start fusing heavier elements, but some giants like Rigel here, they're always fusing heavier elements. So not only is it still fusing hydrogen, it's fusing helium, nitrogen, probably other elements inside its core as well. So bigger giants and supergiants, they're really, really hot on the inside. They're fusing heavier than hydrogen for sure. One other thing, the reason they expand is not only are they losing mass because, fusion uses mass as they burn their fuel, but they also get hotter inside, which that pressure from the heat actually pushes them outwards. So 2 reasons that giants get bigger: more temperature, hotter inside, and less gravity holding them together. Now, all the elements that we pretty much deal with on every day other than helium, I mean, unless you're holding a helium balloon right now, a lot of other elements actually come from these giant stars. So the carbon, the nitrogen in your body, the oxygen you're breathing right now, they all come from giant stars, and usually the supergiants, not just regular giants. So any element that isn't hydrogen, helium, and lithium didn't come from the Big Bang. I'm going to go ahead and tell you right now. The Big Bang only made hydrogen, helium, and lithium, and there's not a lot of that hanging around in our bodies right now. I mean, there's hydrogen in the water, but pretty much everything else had to come from stars. So when giant stars die, they fling a bunch of elements out into space. They fling carbon, nitrogen, oxygen, everything up to number 26 on the periodic table, iron. So elements 3 through 26 come from stars. And dwarfs, let's talk about what happens when they die. So when a low mass star dies, any star that's up to 0.8 solar masses, when it dies, it'll simply just collapse under its own gravity and be crushed into a white dwarf. So small mass stars don't blow up. That's a misnomer. No, they don't do that. Maybe a few layers of hydrogen might escape, like the outer layers of the star that weren't really being held by gravity. They might poof out, but for the most part, the stars just fall in on themselves. And it's what it makes is a white dwarf. So a white dwarf can be considered a dead small stellar object. And it's really, really dense because think about it. There used to be a star there, and now it's compacted into the size of something that's like Earth. So that's really, really small for a lot of stuff. Now, white dwarfs can be up to about 1.3 solar masses, I believe. Don't quote me on that, but it doesn't have to be 1.3 solar masses for a white dwarf. Now, to put the density in perspective for a white dwarf, imagine that you were back at school, like it was last year, and you're sitting at one of those desks. One of those desks, if it was being made of white dwarf material, would weigh more than the entire school itself. So a lot of mass goes into these white dwarfs. They're very, very compact. They've got a lot of gravity. Now, here's a picture of a white dwarf compared to a nearby star. And you can see they're a lot smaller. Notice one other thing about white dwarf. Notice how it's blue in color. So as the star collapses and become a white dwarf, they actually heat up hotter. So white dwarfs are actually hotter than a lot of stars on their surface, but they're not performing any fusion. So what happens is over time, they just cool down. Now let's talk about a medium mass star now. So medium mass stars, 0.8 to 8 solar masses. This would include our sun. So for medium mass stars, just like low mass stars, they will also become a white dwarf. But unlike low mass stars, instead of simply falling down and becoming a white dwarf, a lot of their outer layers of hydrogen and helium will get blown off into space. So they'll fling about half of their mass out into space. Now, we're not talking like explosion. So our sun will not explode when it dies, okay? Don't ever say that again now that you know. It will just poof it out into space. Imagine like just blowing. So it'll blow at its outside layers on the space, and only the core inside, the helium core, will stick around. So what will happen to this gas and dust that was blown out? Well, it could become a new planetary nebula. It can float through the Milky Way galaxy, and maybe a new star will be born from the leftovers of our sun or any other medium mass stars. The white dwarf will also stick around as well, and this will happen for our sun in about 6 billion years. So it'll end its life on the main sequence at about 5 billion, and then it maybe has a couple hundred more million years before this will happen. So that's what happens for a low and a medium mass star. You'll get a white dwarf, and then for medium, a new planetary nebula might form and it'll float off into space. Black dwarfs first. So none of these exist yet. You're going to see these when you're reading the Canvas module. But for a black dwarf, what it is those white dwarfs, since they're pretty much considered dead stars, they're cooling down over time. And eventually, billions of years from now, trillions of years from now, maybe even quadrillions, these white dwarfs will turn into black dwarfs. And so what will happen is they'll run out of temperature and they'll become as dark as space. Now, the reason none of these exist yet is our galaxy, everything, the entire universe is only about 13 billion years old. So if these things take quadrillions of years to cool down, trillions of quadrillions, none of them have cooled down yet. All the white dwarfs that were in the Milky Way galaxy and the universe are still here. They're still white dwarfs. Well, let's talk about these high mass stars now. So the ones that are 8 times more massive than our sun. They got 8 times as much stuff in them. Now, like I said earlier, and like we did in the chat box question earlier, they have a shorter lifetime than the smaller mass stars. And that's only because they use through their elements quicker. Now, big mass stars, they do fuse hydrogen and helium, but inside the core, as you go deeper and deeper, they start fusing heavier and heavier elements. So for a 25 solar mass star, it fuses hydrogen to helium, and it'll start fusing helium to carbon, and carbon to oxygen, and oxygen to silicon, and silicon to iron, but you can't fuse iron. So as I mentioned much earlier, iron doesn't release energy when it fuses. So once a star reaches iron, it stops. Sure, it'll fuse these other elements like silicon and oxygen and carbon, but once that iron core gets too big, about 1.4 solar masses, that's it. The star is done. And so what will happen is this star will go supernova right here. You can see it right here. So compaction will heat the star to 100 billion Kelvin. The star will collapse. As it's being collapsed, it'll heat up. And once it hits that iron core, it'll bounce off and fling most of the star out into space. Now, what happens afterward depends on how massive that star is. So a supernova will definitely happen. For any star bigger than 8 solar masses, you're going to get a supernova explosion. So when that iron core reaches 1.4 solar masses, the star falls inwards, it heats up, it flings stuff out into space, and basically every element above 26, above iron on the periodic table, is made from a supernova. Now, here's what a supernova looks like. And actually, even though this supernova happened in 1987 and was visible, this picture was taken with the Hubble Space Telescope something like 8 years afterwards. So they're still shining bright many, many years afterwards, even though the supernova is long dead and gone. And what that means is, well, I don't want to go into too much, but these elements in these supernova explosions are radioactive. I mean, they've been slammed together, neutrinos that hit them, protons, neutrons, everything's just running into each other. Of course, you're going to get radioactive elements. I mean, this is how elements are made. And over time, it will fade as the radioactive elements decay, but these things can stay shining for thousands and thousands of years. In fact, here's a supernova nebula. So this nebula is actually from 1,000 years ago right here. And it's still shining kind of bright. Now, it's not shining like visible light anymore, but we can still pick it up with infrared light. So a lot, and microwaves as well. So these nebulas that are made from supernovas, they're still full of new elements. In fact, every element above iron, as I mentioned earlier, anything from nickel up to uranium plus is made by these supernovas. It's why we have, elements such as copper, zinc, iodine, nickel, molybdenum. I guess nickel you can get from regular stars as well, but pretty much every element that we care about, other than, carbon, oxygen, nitrogen, anything up to 26, has to come from a supernova. And what happens is, when a supernova happens, this nebula is flung out into space, and new stars can be made from that nebula. That's how our sun came to be, and our planets. Most of our planets did not come from the Big Bang, only hydrogen and helium, and that's not a lot of Earth. So our planet, most of it came from a previous star that died. And pretty much almost every other element came from a previous star. Even lower elements like carbon, nitrogen, oxygen, they still came from stars. They just didn't come from the supernova itself. They were just inside the star when it died. Now, two things can happen after a supernova. Yes, you're going to get a nebula. That happens no matter what. But you're either going to get a neutron star or a black hole. So we're going to talk about neutron stars first. If the star is a lower solar mass star, like 8 to something like 20, you're going to get a neutron star. And you can see it right here in the center. Here's what it looked like, and then 15 years later, they went and took another picture of it. And there's the neutron star. Now, notice it's nice and blue in color. And that's because neutron stars are really, really, really hot. They're more massive than the sun. They're about 1.4 solar masses. So a little bit more massive, but they're way, way hotter than our sun. In fact, I think they're about 1 million to 10 million Kelvin. So they shine white hot. Now, here's a picture for a size comparison of a neutron star. So here's a city for comparison. And you might think, okay, that's huge. Well, yes, compared to humans, neutron stars are big. But they're only about, a mountain range in size. They're not that huge. And compared to a sun, they're tiny. They're minuscule. So they're not big compared to stars, but they are dense, really, really, really dense. So a sand grain, imagine something the size of a piece of sand, taken from a neutron star would weigh more than the entire pyramids. This neutron star right here would weigh more than millions of Earths. They're huge, and they're super, super dense. So neutron stars are very, very interesting. I wish I could go into more, but we just don't have the time. But there's whole other things, like there's magnetars from neutron stars that spin really fast. So if you want to, check them out. Look up a video on YouTube about neutron stars. There's lots of videos. Maybe I'll post one in Canvas, but very interesting objects. Now, there's also black holes, which are also interesting in their own way. And up until 2 years ago, we never had a picture of a black hole.